In our previous lecture, we have seen Kirchhoff's voltage law. Today, we will derive the Kirchhoff's current law from the equation of continuity. Now, you might know that the principle of conservation of charge is one of the most basic principle or the law of nature. So, we will take it as a law only that the charge is conserved in this universe. That is, electric charges may not be created or destroyed. All charges, either at rest or even in motion, must be accounted for all the times. Now, if the time permits, while dealing with the magnetic field, we will show that this electric and magnetic effects are relative in nature, and although the charge is conserved, but if we take the relativistic effects, then we will see that the charge density changes, and because of it, we can explain the magnetic effect in terms of electric effects only. But that will be done in some later lecture. Let us say that there is this volume, and this volume contains a charge q. Now this volume is enclosed by these surfaces. Now I will assume that from all the surfaces of this volume, which is bounded by all these surfaces, a total current I is flowing out. So it implies that if this total current I is flowing out from this all the surfaces like this, like this, like this, so it implies that this charge is going to decay or decrease at a rate given as I is equal to dq over dt. Since charge is conserved, and if there was some charge q inside it and now there is total current flowing outside from these bounding surfaces, then it implies that this charge is decreasing with time and the rate of decrease is equal to this current. So writing in terms of equation, I can write the total current I going outside from the surface which is bounding this volume, the surface which is bounding this volume. So I can write it as I is equal to the integral of j dot ds over all the bounding surfaces, and it should be equal to the rate of decrease of the charge which is inside that volume. That's why this minus sign has come. It implies I can write it as j dot ds over all the surfaces should be equal to minus d by dt of, now I can write q as simply the volume integral of the volume charge density into the volume. Okay, so now if I assume that this volume is stationary, that is, this volume is not moving, then what I can do, I can interchange the orders of this integral as well as this differentiation. They are kind of now independent of each other. I can do either of them in any sequence. So I will take this differential or differentiation inside the integral. Now when I will move this differentiation inside the integral, then this full differentiation will change to partial derivatives, because this charge density can be a function of position, but we just want the change with respect to time. That's why I have now written the partial differentiation. Now I will use this Gauss divergence theorem. So I will write it as del dot j dv dash is equal to minus of dou rho by dou t dv dash over the whole volume v dash. Now since this integral is equal at every point, so the integrand should be equal. It implies del dot j is equal to minus dou rho by dou t. This is the equation of continuity. and it is just simply means that the charge is conserved. Now we can think of it as a definition for steady currents, that for steady currents the charge density does not change with time, that is dou rho by dou t is equal to 0. When the currents are steady or uniform, then the charge density, it does not change with time, it remains the same. So for a normal scenario, a conductor which is carrying current I through it, then if this current is steady, then the charge density on the conductor, it will not change with time, it will remain same. If it, let us say if it was initially neutral, it did not have any resultant charge, that is it had equal plus and minus q charges, then this scenario will not change with time even if this current keeps on flowing. So this is the meaning of steady currents, that for steady currents the charge density does not change with time. So I can write now from the equation of continuity as del dot j is equal to 0. So it implies that the current density for steady currents is a divergence-less vector. It implies that the streamlines or the field lines of this current density will make closed loops similar to the magnetic field. So unlike the electric field lines which originate from plus q charge and either they terminate to infinity or to another minus q charge, the streamlines of this steady current density, they close on to themselves. So this is the difference between the streamlines of a steady current density and electric field lines. Now from this equation I can write using Gauss divergence theorem as j dot ds over all the surfaces bounding this volume is equal to 0. Now this is simply the total current across all the surfaces which are bounding that volume, equal to 0. So it is another mathematical form of the Kirchhoff's current law. Which is simply based on the charge conservation property or the principle. So what does it say? It says that the algebraic sum of all the currents flowing out of a junction in an electric circuit is 0. So in this way we have derived Kirchhoff's current law from the principle of conservation of charges, and this equation of continuity is a very important equation and we should remember it. Now in our previous lecture we have told that in electrostatics there will not be any charges inside a conductor. Now the time has come to show that it is really true. So let us take again the equation of continuity, del dot j is equal to minus dou rho by dou t. Now j is simply sigma E. Now I am assuming that the medium is homogeneous, that is this sigma is not going to change over this medium, so I can bring it outside this del operator. So I will write it as sigma del dot E is equal to minus dou rho by dou t. Now if you remember, this del dot E is simply the Gauss law. So sigma rho over epsilon is equal to minus dou rho by dou t, or I can write it as dou rho by dou t plus sigma over epsilon rho is equal to 0. Now it is just a simple differential equation whose solution is of the form rho is equal to rho naught E minus sigma over epsilon T. Now what does it mean? It means the charge density is going to decay according to this exponential curve or exponential law. So if the charge density, even if the conductor has some charge density inside it which was having a value rho naught at t is equal to 0, then it will decay according to this equation, and within a one time period it will decay to a value which is 1 by exponential times 1 by e times of its initial value, and that time period is usually called as the relaxation time, and its value from this equation I can clearly write it as tau is equal to epsilon over sigma. Now 1 by sigma is simply the resistivity, so this tau or the different term is called as relaxation time is simply rho epsilon. So for a given conductor, let us say for copper, we can calculate its value, and its value comes out to be about 1.52 into 10 raised to power minus 19 second. So you see that this time for copper is very small, 10 raised to power minus 19 second. That is, it is negligible. So within one time period or this relaxation time, the value is going to be decayed to about 36.8% of its initial value. So you see that within no time it is going to get to 0. So we have proved that even if there was any charge inside the conductor, it will decay and come to the surface. Of course, where will the charge go? It cannot be destroyed, so it will come to the surface within this small time frame. And what if this rho naught was equal to 0 initially? So it implies if there was no charge already inside, then it will always remain, this charge density will always remain 0 at any given point of time. Since it was already 0, so this charge density will always remain 0. So it implies that if there was already no charge inside the conductor, then there cannot be a charge at any point of time inside the conductor, even if we consider current flowing through it. So in this way, we have explained another concept, and we have proved that in electrostatics at least, the conductors cannot have any charge inside because this relaxation time is very small. And this quantity relaxation time, tau is equal to rho epsilon, it's an important quantity, and we will see it many times in our study of electromagnetics. So if you find that this lecture is helpful to you, then please share and subscribe our YouTube channel, and also join our Telegram group whose link is given in the description of this video.